Hello, everybody. I can't even say happy garbage day because it's not garbage day at my house. Because if it was President's Day yesterday, which is like a city holiday, and that means all the garbage collection is over a day. So I'm going to be really confused tomorrow when I have to put the garbage out and bring it back in, and then I don't go to campus to teach. It's going to mess up my whole routine. As it turns out, though, I have to come here tomorrow for a meeting anyway, so it won't be completely crazy. But let me let's see, screen share is still not on. I need to do that part next. All right, there. So we have, then in terms of stuff you're working on, I just downloaded all of your Homework 1 accuracy drafts. Every single person turned it in on time. Kudos to all of you. That rarely happens in a class. So thank you for that. Your next thing to do is formative assessment number 2, which I just made up this morning. Another brand new set of questions because we're covering new territory. So that will be due Monday night. You should be able to answer all of them now and for sure by the end of the weeks and classes. The next thing then I think is the not final project outline. We can call it an April project. How's that sound? Because it's not final. It's during April. So let me know if anyone wants to talk to me about that. You should be figuring out what data you're going to use, what variables in the data are interesting to you, what you want to know about them, and who you're going to work with if you choose to work with a partner. It's your choice. Presumably you will contact the partner ahead of time and arrange for this. I'm not trying to play matchmaker or unmatchmaker, as it turns out, but if you have someone that you're already working with on something and you'd like to continue that collaboration, by all means. All right, any logistics stuff that I'm forgetting? Anything else? I think that's all the stuff on the top of my head. Zoomers, we're still good? Okay, I turned off the auto recognize hand gesture thing, so hopefully I won't mute myself, turn off my camera, or otherwise mess something up with my hands talking. But let me know if that does happen. I did not intend for that to happen before. All right, so where we were last week then is entering the wonderful world of structural equation modeling for longitudinal analysis and trying to figure out how all of the ideas, vocabulary, and notation that we've been working on translate into this framework instead. So I think, if memory serves, we had gone through all of the multi-level SEM versions of this stuff. Does that sound right? So to me, that is an easier transition because, say, for instance, when we have a model like this is slide 8. This is an unconditional random quadratic model. It's a picture, but otherwise everything is kind of the same because you're still talking about long data. So you have a column for your outcome variable per occasion, per person. You have a column for your time variable, for instance, and a column for your time squared. And then the relationship between each of these predictors and the outcome can be captured either as a fixed effect, which would be conveyed just by this path, or a random effect, which means the fixed effect is the mean of a latent variable and the variance around it is the random effect variance. So that's the biggest difference, I think, is we have these beta things as placeholders for the fixed and random effects to be defined and predictors in there. The betas are latent variables, from this perspective. This is beta 0. That's what this circle means. This is beta 1 and this is beta 2. And they mean it because of the way that we've either defined it as the intercept for the outcome or as a slope for basically this path right here is brought into the model via this latent variable. So it's not as much of a switch in notation and ways of thinking about it as the single level SEM. But we looked at this. So this picture, let me just flip through a couple slides here just to get us reoriented. Is that okay? Can I assume that we don't remember everything perfectly from Thursday, which, that's 5 days ago. I don't remember what I did yesterday. So this model, is there any reason why I would want to fit this model using a multi-level SEM package as opposed to Elmer or Stata Mixed or something like that? Can you think of any reason why this particular model would need to be done that way? You're hesitant, and that's good, because the answer is no. There would be nothing to be gained from this particular model. There could be something to be lost, though, in the sense that I'm forced to use maximum likelihood with no degrees of freedom instead of REML with denominator degrees of freedom. And by the way, Bayes does not fix that, because the likelihood function that goes into the Bayesian process is the ML version, not the REML version. So there's a lot of work looking at, recent work, I would say, looking at what Bayes can bring to the problem, but it doesn't just fix it unilaterally. I would say that. The jury is still out because it matters what priors you use to some extent. Let's see. This model right here adds, this is slide 10, so I'm adding a level 2 time invariant person predictor, my level 2x, and I'm allowing it to predict the intercept, the linear time slope, and the quadratic time slope. So the gamma 1,1 paths and the gamma 2,1 paths we would normally call cross-level interactions because they represent level 2x by time, or time squared. Would there be any reason to fit this model in multi-level structural equation modeling software as opposed to multi-level single univariate column software? Multivariate, yes, there could be one reason why I would want to switch. My reason is a two-word phrase. First word starts with M. Second word starts with D. Missing data. Yeah, this thing right here, it's not in the likelihood in a univariate multi-level modeling software package, meaning I can't have missingness on it. So that would mean, because it's a level 2 predictor, that anyone who does not have this variable gets all of their occasions kicked out because it's missing for every row of that person. If I wanted to bring it into the likelihood, then I pretend like it's an outcome by asking the software to estimate its mean, variance, or covariance with other stuff. That means I can have missing data on it, but it also means that I'm making distributional assumptions, univariate normal in this case, for it. So that would be a reason, missing data. What about this model, slide 12? Could I do this in Elmer? Oh no, look, which way did the arrows go? This is the one where it's backwards. So in this picture, level 2x is an outcome of the intercept, linear time slope, and quadratic time slope for another variable y. And then I have my Kluge equation to try and describe what that would look like, where I have fixed effects from the intercept in each of these things to that predictor. So no, there is no way to do this in a standard univariate multi-level package because it only allows you to predict one column at a time. This would require you to predict 2 columns at a time, multivariate. And this code to do that would look like this, where the fourth line on the bottom here of slide 12 is describing y, lin, and qua as the names of these circles here as predictors of level 2x. So remember, in M plus syntax, the y outcome goes to the left of the on and the predictors go to the right. The last line is all you would need if you wanted to bring level 2x into the likelihood but not actually predict it. If you wanted to use it as a predictor but have missing data, you would need the last line here. Level 2x in brackets means estimate its mean or its intercept. Level 2x outside the brackets means estimate its variance or its residual variance. So yes, this would be a reason to move to this framework, to do something like this. Questions? Yes, and not me this time, from someone else. Go for it.
I just wanted to be clear about the relationship between what we're doing on this slide with this model and what we did on the last slide with the last model. So when you say the reason to move to a multi-level structural equation modeling framework on the last slide was because we wanted to have missing data on this level 2 predictor variable.
Yes.
Is this a step, is this not a step that is going on in the background of that model where, I'm just trying to understand how when you say treating the level 2 predictor as an outcome is wrapped up in moving to the multi-level structural equation modeling framework, and why what you said before is different or the same thing as what's on this slide.
Okay, so let me go back to the previous slide. So slide 11 has level 2x as a predictor of the intercept, linear slope, and quadratic slope of y. So it's moderating the growth curve of whatever y is happening over time. You could fit this model in Elmer, but the downside would be that you can't have any missing data, because basically the process of maximizing the likelihood works on the residuals. You have to be able to know what y hat is to figure out what the residual is, and you can't get a y hat if you don't have the predictor. If you wanted to still have it in the model as a predictor but have missing data, you would have to bring it into the likelihood by estimating its mean or variance, even if nothing is predicting it. And that would turn it into a joint likelihood where it's maximizing the properties of x and y simultaneously in addition to their relationships. So from an estimation perspective, it's an outcome in the sense that it's like everything for it is being solved for at the same time, but in a modeling sense, it's still a predictor of other stuff. So this is if it's a predictor, this is if it's an outcome, but the bottom line here on slide 12 is what you would need to bring any variable into the likelihood that's not already there. What you do with it as a predictor or an outcome is up to you from that point. Does that help
Okay,
at all?
got it. Yeah, I think so, thank you.
Yeah, it's confusing because then you get into like people's use of like the terms exogenous versus endogenous, which maps onto this sort of. But the distinction that matters is this variable in the likelihood or not? Like, do its summary properties have to be found and recreated by the model or not? And if they do, then there's distributional assumptions and you can have missing data. If they don't, there's no assumptions but no missing data.
I have a question. So, but from the previous slide,
Okay, slide 11 again?
yes,
Okay,
we are talking about bringing the missing data to the likelihood, but from the code, we are not doing that here.
that is correct. In this code, I would have to add the bottom line to this slide, and then it's a predictor, but it's in the likelihood. Yes, that would be the extra component. Another question from the Zoomers, what is an example scenario where you would want to ask whether random effects predict level 2x? So is the question about slide 12, like when would you need to do this? Yes, okay. If level 2x happens later in time, would be an obvious case. So the example that I gave in class is, let's say that y is reading ability during elementary school, and you want to look at how individual differences in how quickly children learn how to read predicts high school graduation or admission to college, or some other like distal outcome is the phrase they use for that. Like something far away is distal and something that's closer in time is proximal. Then this would allow you to do that. This could be any other person level variable that's only measured once. Ding, ding. That's when I would do this. What I have done in the past, though, so I have a paper, actually, I'm like 6th author on or something because it was a student project that turned into a paper after many, many years. It was someone who basically wanted to do this. The y variable in the paper was children's changes in their babbling, like the ratio of consonants to vowels is apparently indicative of something. And they were looking at change during like from 1 year of age up to like 3 years of age in this babbling behavior, and they wanted to predict some kind of academic outcome like in 6th grade, like further in the study. So she wanted to do this. The problem is that there were 12 children in the study. This is not going to go well. So I convinced her, even though her question was slide 12, to do slide 11 instead so that we could do it in a REML universe. And because there was no other variables involved, I argued that if y predicts x, then x should predict y, and that this would make sense. The reviewers, of course, had to argue about it. So, but we won, and it's published. So yeah, if you have 8 people, I would not recommend trying slide 12. I don't think that's going to go well. But, all right. Does that help answer the question about when would we do this? Yes, thumbs up. Okay. All right. Then we did this stuff, the SEM side. So the big difference is wide data instead of long data. So in these pictures and in the equations, we're thinking about every single occasion as a separate box for every variable. So the notation that I've introduced here, the first line is like a generic representation, and then these would be the 4 equations to depict the 4 boxes. So right away, you have to know how many occasions you have in order to make a diagram, whereas we didn't have to know that in that multi-level version. It was just one box regardless. So I did the translation here into how we end up with this type of model with this type of situations, starting from a single factor model into 2 factors. So each factor would have a loading, as it's called, which is just a slope describing the extent to which that factor predicts an outcome. In factor analysis, each outcome has an intercept that gives its each predicted outcome whenever the factors are 0. To fit these models to be able to take those means and push them up to the factor level, we shut that off. Rather than talking about the fixed and random effects as separate ideas, we lump them back together in their placeholders. We swap out beta 0 and beta 1 for my f's, and then rearrange the loading so that they show up in the back, and then we're at the same thing as the level 1 model here. So this to me is the weirdest part. It's the idea that we used to have a slope in front of f2, but now what we used to call the slope is the factor. So time in this case is introduced via the factor loadings, not via a variable. And the same idea though, beta 0 and beta 1 are latent variables. Their means carry the fixed effects, and their variances are the random effect variances. So this is like the trickiest part, I feel like. Once you have your head around this aspect, then everything else is not as bad. So let me pause here and ask if there's questions about this. And of course, reload. So how do I know what these latent variables mean? Is dictated by the pattern of loadings that I assigned them. The reason that this is an intercept is because I stuck ones here. Like in factor analysis, we don't put constraints most of the time. We let the loadings be whatever they want to be, assuming the factor is identified. That's not the case here. So you know this by another name, by the way. What do you call it when a factor has equal loadings? Yeah, tau equivalent or a Roche model. And the reason that these are ones is because we're estimating the variance of this. If I had fixed the variance of the intercept to 1, then these would all be equal, but they'd be some estimated quantity. So in this world, we always estimate the factor variances, and we usually estimate the factor means as well. We want all of the information about the means of these outcomes over time up here. So another way of saying it is that the original intercepts that we would have had of these 5 boxes, they are trying to be recreated by the mean of the intercept factor and the mean of the slope factor. If the model does a good enough job, then rather than having 5 means, we have 1 fixed intercept and 1 fixed slope. Likewise, all of the original covariances among these outcomes, we are saying is because of the random intercept variance and the random slope variance. And if that fits, we shouldn't need any more. Yes, question?
So would the factors be the G matrices or the G matrix collectively?
Yep. Yeah, here's the mapping. So in factor analysis terminology, what we call G, level 2 random effect variances and covariances, is the factor matrix of variance and covariances, which phi or phi, take your pick. Z is the factor loadings. So Z is normally how each person, like we tell it which occasions a person has. R is the error matrix, so that's psi in SEM terminology. So if we map everything, let me see here. Nope, I don't have that picture yet, it's coming. I have another picture where everything's mapped on there. But yeah, so V is everything put back together again. That's the analog of sigma. Like the model predicted variance covariance matrix all puts back together again. Alternatively, if I don't have a slope factor, What I could do is estimate the intercept for each of my 5 outcomes here and fix the fixed intercept, the mean of this factor, to 0. That would give me a saturated means random intercept model instead. We will see variations of that when we get to SEMs with cross-lagged effects. A lot of those models are set up that way. They deliberately estimate the mean for each occasion because they don't have data in which a slope is relevant. So they just control for whatever the mean difference is and don't worry about it from there. That's an empirical question, of course, whether that's true. Okay, let's see. Did we get into code? I think we did. No, we did not? A little bit? Okay, there's a disagreement. That means that we need to go back over it again. The only question is whether it's a review or a re-go over situation. No, I'm sticking with that phrase. Is re-go over is a term. It means present it as if you've never heard it before. Re-go over. So to fit this model in code, so I have an example with our accelerated, the longitudinal study, but this is a generic example. So I'm fixing the intercept factor, which I've named int, with the loadings in M+, it's at to fix a loading, or anything to make it not found, but at that number. I'm calling the second one lin, and it's fixed to the differences in time that there would be between these occasions. So that's key. This is assuming that these are equal interval. What if instead the last box was like 3 units in time later?
You have to adjust the loadings.
Yeah, so if it was 3 units in time rather than 1 unit in time, and I would do y4 at 6, because that's how much time would have passed if there were 3 units between these boxes. So you control the meaning of this factor via the pattern of loadings. This is a linear slope because of the way that I set the loadings. But I could fit other kinds of not linear slopes by changing the pattern of the loadings accordingly, or even letting it figure it out. That was where I think we ended up, is starting the idea of latent basis. It's quadratic. So I know that this is a quadratic slope because it is the occasion squared for the loading. And the same thing would be true here. If the last occasion were 3 units in time, I would change the linear loading from 4 to 6, and then 6 times 6 would be 36 for the quadratic. What if I wanted to do a piecewise model? Could I do that? Sure I could. I would do, let me get Excel out real quick here. I always like to do my piecewise coding in Excel. So what if I had something like, this is time, we started at 0, 1, 2, 3, 4, and I wanted to fit a model where this was like slope 0 to 2, and this one slope 2 to, 4. If I put the intercept where the knot is, where the breakpoint is, let's do that, be 0, 0. Then this would be 1, 2. This would be 0, 0. This would be minus 1, minus 2. And this would be like 0, 0. So that would give me change covered by that variable, change covered by that variable. So these would be your factor loadings, if that's what you wanted your 2 circles to mean. So it's completely up to you what pattern of change you want to introduce. You do it through the loadings. Yes, sir?
That would be the Z matrix.
This is the Z matrix. The Z matrix is the loading matrix in this world.
I'm trying to think in Bayes land. They have the matrices and not loadings.
In Bayes land, you still have loadings. I'm quite certain of it. They just all have priors on them, right?
No, but the way you define it is in a matrix instead of like, it's craziness.
Yeah, not it on that question. I don't think in terms of matrices. But I can tell you what the scalars would be that would go into like the Z matrix is a matrix. But the problem with this approach is that we have to assume that this holds for everybody equally. If we hard code it into a loading, there's no room for someone to be like, hey, I didn't show up at time 1, I showed up at time 1.2. Well, Well, too bad. It's time 1 for you because I have the same set of loadings for everybody. That's one of the big downsides of this type of strategy. So yeah, if I did that type of coding scheme instead, then this wouldn't be linear and quadratic. It would be first half, second half change, something like that. Let's see. Level 2 predictor. Same thing. We have an equation here that includes what we would call intercept prediction, linear and quadratic, cross-level interactions. I can turn the arrows around. This is slide 19, where I can have level 2x be another outcome of something else. By the way, what do you think it would look like if I had a time-varying outcome or time-varying predictor? What if x was a level 1 variable? How many of them would I have?
Or 4.
5 in this one. 5 in this slide. I'd have 5 x boxes. And what if I had a third variable, z, that varied over time? Another 5 boxes. So the diagrams get cluttered real quick. But I think because each occasion is a separate box, it makes it easier to accidentally smush effects of level 2 and level 1 prediction together. So I will show you this. This is the next unit after this one. I've got actual pictures from the M+ manual and from the Levon manual of what not to do. Like, they made pictures. And they've been there for years and no one has changed them. So I'm like trying to get that to be fixed. Someone needs to fix that. But yeah, any box right here is just one column in a data set. So it could be a single outcome that's at level 2. It could be like the time 0 version of a particular variable. So I have subscripts on my boxes to try and, like, this is why 0, 1, because everything is I in this notation system because everything's on one row. So it gets tricky to keep track of what exactly this stuff means, I think. All right. So here is code, for instance, what it would look like to do a random quadratic model with level 2x as a predictor and M+ on the left-hand side. This is what it would look like if level 2x is an outcome. And the difference is just this last 2 lines here. Everything else would be the same. So in each of these cases, we have defined our 3 factors. We have fixed all of the loadings to indicate what they should mean, whether they're intercept, linear change, or quadratic change. Fixed effects are inside the brackets. Random effect variances and covariances then are when you list it by itself. With is a covariance. We have to shut off the per occasion intercepts to make this work. And I'm constraining the residual variances at level 1, so the R matrix to be the same over time. That's a constraint that's empirically testable, by the way. But that's typically what we start with, at least in multi-level land. Here's the Levon code. I think this is where we stopped, if memory serves, right? So I remember like saying, here's some Levon and I'm done for today. But for those of you who are using that as your SEM framework, this is the translation into that. What makes this look different than M+, by the way, factor loadings that are fixed in Levon are stars. Factor loadings that are free in M+ are stars. I don't know why they did this. I do not know why they did this, but the @ symbol apparently in R was already taken for something else, is what I'm guessing happened. That's the same reason why we have squiggles for everything here, is because equals was already taken. In this code, 1 squiggle is an intercept, 2 squiggles is a variance or a covariance. If it's the same word on both sides, it's a variance. If it's different words, then it's a covariance. That's what it is. And to add things together, like to have multiple predictors, you put plus signs, which looks a little weird, but you do the same thing for the factor loadings. Even though it looks like you're adding things together, you're not. That's just the code. So, whatever. Okay. So, good news, bad news for using single level SEM to fit some of these models. If you have unbalanced time, this is the bad news part. So you need something that is called more generally a definition variable. in your software to be able to fit unbalanced time. MX as a package, OpenMX, and M+ are the only ones that I know of that have this. There may be others, but I don't know of them. I looked for this in Lavaan and I was unable to find it. Basically what you need is the capability of saying, no, don't call this 0, 1, 2, 3, 4. I need you to pull what the loading should be for each person out of a column of the data set. So what you would need to have is 5 columns, one for each occasion, where the value in the column is exactly when that occasion was for that person. So if somebody comes in, the first time they come in is time 0, then they were supposed to come back 1 month later, but it was more like 3 weeks. Then this one would need to switch to 0.75 for that person. Someone else came in 5 weeks later, this one needs to switch to 1.25 for that person. That's the idea. So rather than saying the loadings are fixed to these constant values, you say use this variable rather than a constant. And the option for that is called T-scores in M+, and I'll use that in my example. This is not a thing in multi-level SCM land. This is not a problem, because in multi-level SEM land, you're back to long data where you already have a column. You called it time. So there's no loadings that have to be specified as constants. It's all just pulling information from a column anyway. 1 column, not 5. One of the things, though, that you can do very easily in this type of framework that is probably possible but more cumbersome in a multi-level SEM framework is to fit what's known as a latent basis model. That looks like this. So I'm on slide 23 here. If you have relatively few occasions but a linear model is not going to work, then you can ask your data what kind of nonlinear function they would like and give it to them. So what I'm doing is fixing 2 of the loadings. 0 and 1 are the values that I have in this example thus far. And then I'm asking it to figure out what the other 3 should be. The way that you would interpret this is 1 is like all the change that there is. The question is, how long did it take to get there by each occasion? Where these would be equal if it were linear, equal distances between them, and if it were nonlinear, it would be something else. So if you had a change function, for instance, where there was a lot of change right away, and then it slowed down, your loadings might be something like 0, 0.6, 0.8, 0.9, 1. You can think of the loadings as the proportion of the total change that had happened by that point. If you had a function that went up and came back down again, then you might have something like 0, 1.5, 2, 1.51 or something. So I like this approach anytime that you're intending a time slope to be a predictor of something else, because then there's only 1 and not 2. Like if you have a linear time slope and a quadratic time slope as predictors of something, they're going to fight against each other. It will be very tricky to figure out what their unique contributions mean because they're so highly related. So this is one way to get nonlinearity, but not have it take multiple types of slopes to accomplish. So the choice of your constants are arbitrary. Another alternative would be 0 for the first one and 4 for the last one rather than 1. And that would give you the amount of change in the same time scale as you have occasions. Intercept at the beginning is not necessary. You could put the 1 here and the 0 at the beginning. And that would be like maybe -1 to 0 or something if you wanted to keep it the same. So this is useful in situations where you don't have a lot of data, but linearity is not a plausible assumption. So I'll show you a couple examples of those, I think, as well. I note that these loadings can also be random rather than fixed, and there's an article about that on your reading list as well. Question, if we use a piecewise model, can we use a latent basis to allow the model to have different loadings in each phase? Yes, if you have enough data. You'd have to have enough data within each piece to be able to get a good estimate of the loading. But theoretically, there's nothing stopping you. Yeah. And this is what a latent basis model would look like in M+. The difference is that I have stars in the middle 3 occasions where I used to have constants. So it's going to figure out what the change function should look like and then allow individual differences in that function, whatever shape it comes up with. And here's what it would look like in Lavaan. We just have nothing in front of these. So that means you figure out what the loading is. All right. Broadly speaking then, I think this is the last slide, right? Yes, it is. So this is trying to summarize pros and cons of how these different approaches. So we started off longitudinal analysis via univariate multi-level modeling. I start there because it's the easiest transition from the world of regression, which is usually where people are coming from. In that world, person dependency, the idea that there's correlation of occasions from the same person, are captured by what we call random effects and levels of analysis. So we talk about random effects at the person level. If you had people nested in groups, you might have random effects at the group level simultaneously. Because time is a column in your data set, you can have whatever occasions for whatever person and no one cares. It works just fine. Another pro is that it has REML estimation and denominator degrees of freedom, which means that you'll get more accurate results in smaller samples. Big cons, though, random effects can't be predictors and predictors can't have missing data. MSEM, as it's called, works very much the same, except you can predict more than one column at a time. It's multivariate rather than univariate. So that allows you to have missing data on predictors by bringing them into the likelihood as outcomes. It can be better for time-varying predictors. This is our next unit. So to foreshadow, the limitations of univariate MLM really start to show up in the world of time-varying predictors. Because on the Y side, you're allowing the model to figure out how much of the variance is between persons and within persons in Y. But on the X side, we're going to have to do that with boxes. We're going to have to literally carve up a predictor into the between part and the within part and then see how it relates to Y. And it seems awfully arbitrary to carve it up ourselves for X, but to let the model do it for Y. Like, why wouldn't we just let the model figure out how much is between and how much is within? Because we can't do it in the software is the answer to that. So switching to an MSEM approach where we can have multiple outcomes allows us to do what is known as latent centering, which means treat X like an outcome and let the model figure out its variance. Also easier to include random slopes in this framework. It is possible in SEM, but it's a little bit tricky. So SEM is much more common, but it's a multivariate wide data structure. May not work for unbalanced data because factor loadings have to be used to convey how much time has passed. It does allow you to easily test longitudinal invariance, which is the new example that I have, but it makes it easier, I think, to smush effects together. So we have started talking about this with the idea of cohort effects and age convergence. We'll head more into that with respect to other kinds of time-varying predictors besides age as well. So there, done. Hooray. Questions or comments?
Lisa, I had a question just to be sure I was understanding the problem of time-varying predictors and univariate MLM versus MSEMs.
Sure.
So you're saying the biggest issue is that in univariate MLM, we arbitrarily partition the variance in some time-varying predictor by centering on a baseline, or centering on like an initial score, some sort of constant person centering. Whereas MSEMs allow that centering to be determined by the model, just as it does for Y in univariate MLM.
Yes, so the predominant approach to addressing time-varying predictors or level 1 predictors is to do, in longitudinal, it would be called person mean centering, where we will take each time-varying predictor and subtract the person's mean of their predictor across observations. And then one predictor, it has purely level 1 variance in its box. The person mean then is the level 2, purely level 2. And we would put separate fixed effects to prevent smushing from each of those boxes. But it is arbitrary to create observed variables for one half of the model and latent variables, as it's called, random effects and residuals for the other. Another pattern is what happens if your time-varying predictor itself has individual change? How are you going to get that box out of it? There's no way to do that works well. So if you have a predictor that itself needs a growth curve, then you really need a multivariate approach. Just having one thing be predicted is not going to work at all. So that's where it starts to fall apart. Given enough data is the caveat that the more things you have to estimate, the bigger the sample needs to be to do everything at the same time. So as you might expect, if you have less data, your results will be noisier, I would say, more inconsistent across samples than if you have, than if you're nailing stuff down to boxes. But we'll talk more about that later. This is just sort of like putting out there, generally speaking, what are the pros and cons of these different approaches. Okay, anything else? Okay, do you want to see the single level SEM code for the other example, since we did that one before? Okay, so this is example 2, part 2. We went through this with the multi-level SEM code. So now I want to show you what the single level code would look like for, I think, 4 different models or so. That should be about enough. So to recall the story, we have 5 occasions of data, 2 years apart. These are older adults, and we have a predictor of years since birth at the first occasion as cohort in these examples here. And we're doing the good kind where we're using time as the level 1 basis, so nothing is screwed up. Empty model. 3 parameters: fixed intercept, random intercept, residual variance. So in MSEM, we did that. Do you want to go back over the MSEM, or you feel like that's okay? Stick to single level SEM is the new thing. That work? Okay. Let me know otherwise if you have questions about that. We did go over that before. So the first thing that I have to do, if I haven't already done it in a separate package, this is page 2, is change my data format. So M+ has long to wide and wide to long. That does exactly that. And if I only have a couple of variables that I'm dealing with, then I may do this. But if I have a whole bunch of variables that I need to transform, I'll probably do it in SAS or some other software package. You get into weird order of operations problems with centering and making new variables in this thing. But the way it works is you tell it what your old columns are. So I had a column called recall, that's my Y, and I had a column called time, and I'm saying turn them into these columns. So the numbers on here, I chose to convey how far apart in time they are. It's 2 years apart, that's why it's 2, 4, 6, 8 as opposed to 1, 2, 3, 4, 5. Same thing with the time variables. You tell it how people are organized, so I have a column for person ID, and then you tell it how level 1 is organized, and I gave it the values for what these are in this case because that's what occasion was in the prior data set. Then, counterintuitively, we read in the original data. So the variable section here refers to the names in the long file because the names are not part of the file. The first row is just starting the data. So it's going to use most of these variables in restructuring it, but these are the originals. Then they use variables telling it which columns to actually put in the model are the new restructured ones. So this is confusing. Names, old data, goes up here, gets transformed to wide, and then these are the columns that show up in the analysis after the transformation to wide. Missing data, of course. I'm using regular flavor maximum likelihood to keep the results the same across all the packages. And I'm asking for the standardized solution, which is an SCM thing you can do when you're not using t-scores. I did that to make a point, which I'll show you in just a second. Model, then, is where you tell it what you'd actually like to have happen. So this is an empty means random intercept model that I'm fitting here. First thing I have to do is shut off all of the intercepts for the original 5 variables. I am also telling it to take all 5 of my level 1 residuals and have them the same variance across time. So I'm constraining this to be a diagonal R matrix with equal variance. These 2 lines are going to stay the same throughout all of the models. By the way, M+ understands that I don't have 9 variables here with the dash because I told it what they were up here. So it's not going to try and fill in the missing ones of the 0 to 8. It understands that this is my list. Then I'm setting up my intercept factor. I'm calling it int, and I'm saying it is measured by these indicators with all the loadings fixed to 1, the @ sign. In the level 2 model, I'm referring to the mean of the intercept factor, which is going to be its fixed intercept, and the variance of the intercept factor, which is the random intercept variance in G. Okay, with me so far? Zoomers with me still? Cool? Log likelihood value. So bigger is better in log likelihood. Remember, log likelihood is height. -2 times the log likelihood is shortness, in which smaller is better. The output for this is much longer because of all of the constraints being listed. But this is the part that we would always start with. Make sure that it's doing what you told it to. Go through and see if your constraints are actually being enforced the way you want them to be. A lot of problems show up with that step. So these are loadings that are fixed to 1. That's why they don't have a standard error. And do you remember what 9999 means? Did I talk about that? Not a number. It means can't divide by 0, don't know what this is, because 1 divided by 0 is undefined. The mean of the intercept factor, what do we call that thing? That's my fixed intercept for recall. Yes. The individual 5 intercepts have been shut off at 0. The variance of my intercept factor, that's my random intercept variance, which would be in G. Here is my residual variance for the outcomes. Note that that's the same number, meaning that it enforced my constraints correctly. This would be your R matrix residual variance on the diagonal. Usually we look at the unstandardized solution, but I also included the standardized solution so that I could get the R square for this variable. For bonus points, what is that?
The variance explained for the factor.
R square is variance explained, although I got to put air quotes around explained. I'm going to change that to attributed to. There's your clue. What is 0.669 telling us? It is a word you know. That's intraclass correlation. Yeah, so that's the proportion of the total variance that is due to the random intercept. Another way to think about it is explained by the random intercept, but even though I wouldn't use that phrase, yeah, that's my interclass correlation. If I took the standardized factor loadings and multiplied them together, that's what I would get. The predicted correlation between any 2 occasions. Yep. So yeah, that's my interclass correlation in this model. Adding in 2 fixed slopes for linear time and quadratic time. So 2 new parameters, both just fixed effects, no random slopes yet. Here's the MSEM stuff. Here's the SEM stuff. Everything is the same this much, except for the title. We have a couple new things in the variable section. The use variables has picked up time as separate columns. So this is the long to wide transformation of my time column, where they were supposed to come in at like time 0, time 2, time 4, but they didn't exactly come in at those times. This is exact time saved in these columns. And here is something brand new that I keep talking about and haven't shown yet, t-scores. So it's an option. What columns should I use to build the factor loadings out of, is what it's asking. These columns, please. There is a dedicated way to put it in that they recognize your intent to build a growth model. So this bar thing, we've seen this before to define a placeholder. This is like by, except that all I'm listing are the outcome variables and then at, and then the columns that I gave as the t-scores up above. And it knows, just based on this much, if I put 3 names here, that I want intercept, linear, and quadratic. It's like a built-in function that it's anticipating. I don't actually think I can write it out otherwise, because I'd have to explain that the first time through these are all fixed to 1, in which it doesn't matter which exact time is, but the second time through they're not fixed to constants. So there's no other way to write it other than this at feature. So these are the names of my latent variables, where the mean of these are the fixed effects. So fixed intercept, fixed linear slope, fixed quadratic. Intercept variance, and then lin at 0 and qua at 0 is to shut off their variances because they're not in the model yet. So now we have means. Those are my fixed effects. So they're the means of the latent variables for the intercept, the linear slope, and the quadratic slope. They're called means because they're unpredicted. Intercepts are still 0. My 3 potential latent variable variances, only one being estimated. So int is my intercept variance. The rest are fixed to 0 because I told it to. And then R matrix residual right here. Looks like I forgot one. There. I'll fix that later. There should be one more. There. Ta-da. Now I'll have to squish this all back together again to make it fit. There we go. Cohort. So I'm adding cohort and cohort squared as a predictor of the intercept. And then I'm adding what I would call a cross-level interaction of cohort by linear time. MSim, scrolling on forward. Regular sim. So use variable now has 2 new entries. This is age at time 0 centered at 84 and the squared version. I made those down here. So define, you can make new variables. If you make new variables, they must go at the end of your use variable list or you will get yelled at.
I just said, oh.
Yep.
That might be why I'm getting some errors.
That
when
could
I'm running
be.
some models.
Yeah, it has to read all the variables that are in the data first, and then I think it watches for this to add to the list of possibilities, and then it sticks these, so they have to be on the end because they don't exist yet. It's an order of operations problem, I think, is what it boils down to. So yes. By the way, this, you do have to literally make any kind of interaction variable to be used as an observed variable. So you have to make the squared version or 2 things that interact yourself. Latent variable interactions are defined differently though, but anything that just involves an observed variable you have to make. So then, after we tell it to add these 2, where do they show up? What's new? See, it's 128. I'm taking pity on everyone. What's new? Yeah, the last two. So note the placement here on the left-hand side of the on is what's being predicted. So int and lin are variables that are being predicted by cohort, the linear effect. Intercept is the only one that's being predicted by cohort squared. So these would be this one right here, that's my cross-level interaction. Age is predicting the linear time slope. The effect of linear time is systematically varying in this model, though, because I don't have a variance to go with it yet. Those are forthcoming. Survey says, note that even though I wrote it last, it shows up first. M+ has an internal order in which it returns parameters that has nothing to do with the order in which you list them. Ons are usually first. So now, note the placement of some weird stuff here. Qua, which stands for quad, is under means, whereas int and lin are under intercepts. Do you remember why that is? Quad isn't being predicted, exactly. So this is an unconditional. The way that I would say it is that this is the fixed quadratic time slope for everybody, unconditionally. Whereas this is the fixed intercept specifically for people who entered the study at 84. Likewise, this is the fixed linear time slope specifically for people who entered the study at 84. So that's why it's labeled as an intercept, is because it's a factor mean that's been predicted. It sort of makes sense if you go back to the way that we would write the model right here. Here's my equation for the linear time slope. Gamma 1O is like the intercept of this little equation. It's the starting point for how you make beta 1. Although this is what I would call the fixed intercept, this is the fixed linear time slope. But they're both labeled as intercepts on the output, whereas the fixed quadratic slope is labeled as a mean because there's nothing else predicting it. Said differently, the quadratic time slope is being predicted by like an empty model. Mean only. I know. I know. All right. Let's see. Yeah, I think we got everything. So then these two, this is cohort on the intercept, the linear and quadratic effects of cohort. So the older people start out higher or lower? We'll throw you some softballs. Older people start out lower, and the effective age slows down a little bit, less negative, but not significantly so. Two-tailed p-value out here. Let's see, what else? Likewise, variance of qua versus residual variance of int and lin. Same designation. Variance is for things that are not predicted. Residual variance is for things that are predicted. Residual means leftover in this world. It doesn't mean like level 1 residual. It means leftover. So I have a note that some of the numbers are getting a little bit off, and I think it's because of how the estimation works with t-scores, but you would come to the exact same conclusions between the two. Last but not least, adding a random slope for the linear time slope. That was the next one that I did. And so this part is all the same. This part is all the same. So I'm not introducing any new variables. I'm only introducing a new parameter of a variable that's here. Okay, spot 2 changes. What's new? I'm, Lynn,
Sorry.
go ahead.
Not fixed to 0.
Yep, the not 0 is gone. The with one, yeah. So here's what's funny. This is a default in single level SEM. It is not a default in multi-level SEM. By the way, in some of my code, you will see stars everywhere, like this. That means the same thing as not having a star. It just means it's estimated. The real difference is whether there's an at sign. At means fixed. If you want to provide start values, though, that's what you can do with the stars. Like if I want to provide a start value for the fixed quadratic slope, say of 0.5, I would do it like that. And so the stars are useful in that regard. Generally, these models won't need it for fixed effects. Potentially, they would for random effects.
When you say a start value, what do you mean? I don't think I'm following.
A start value is where the iterative search algorithms begin looking for what something should be. So if you have a model that's taking, say, I don't know, what, 2 days to converge, right, Vladimir? He has a data set of like 30,000 observations, and every time he runs something, it takes like 2 days to converge. If you're in that sort of situation, start values, particularly for the model for the variance parameters, can help it figure out where it should be faster. So.
If we don't have 30,000 people, we should just ignore what you just said about stars at the risk of feeling a little broken.
It doesn't hurt anything to put a star there if it's an estimated parameter. But the only thing that makes different is the at.
Yeah.
The at means you're shutting it off.
Okay.
Or fixing it to something. At 0 means off.
Yeah.
Like if I wanted to say, I want my factor variance to be 1, then I'd go 1, and that's at. But in Lavon, it would be star 1. I know, just to mess with you. And the people who made Lavon know how to use M+, so I don't know why they're being mean. I think it's just mean to go backwards, but anyway. So yes, in some of my, when I first start teaching with M+, I tend to stick stars everywhere to make a point as to what's free and what's fixed. But in these models, everything is free unless specified otherwise. So, yeah, so the not at 0 means I'd like a slope variance, please. And that means that then I need to add the covariance between the two, which is added for you in SEM, but not multi-level SEM, which is why I write it. So the new things here, that is my covariance. So that's my intercept slope covariance that would normally be hanging out in G. And then the new leftover variance for my linear slope is down here under residual variances because it's being predicted by cohort, which is right here, the fixed effect that goes with that. So this means that I put it all together. Right here, the intercept linear, that's my fixed linear term. So initially, people are going up. The effective cohort on that is positive, which means initially older people are going more up. Yeah, but they start out lower. So it's like a different shape. So they start out lower and go more up to start with. More upper. And did I try? Yeah, I tried the interrobang model. I did. By the way, the interrobang model is adding a random slope at level 2 for cohort to unsmush that. In this case, it's just introducing level 2 heterogeneity. And I don't think it worked. Yeah, this was the giant error message I got out of the MSIM version. Yeah, and SEM was like, what are you doing? No. And that was that. Okay.
M+ is aggressive with their error messages.
Well, the all caps yelling thing is that's one. So this is where sometimes it tells you if there's a problem, sometimes it tells you where the problem is, and sometimes you have to figure it out. So some error messages will say things like, problem with parameter 29. So you got to figure out what parameter 29 is. The way to do that, by the way, is a piece of output called TECH1, TECH1. that provides basically all the input matrices of where all the parameters are, and so then you just search for where 29 is and then try to figure out what the problem must be based on that. But it's telling me here that the problem is asking for a level 2 random slope of a level 2 variable, which, unsurprising, why I would think that's a problem. Okay.
I have a question
Mhm.
about character limits in
Yes.
N+.
Mm-hmm.
I'm getting to a point where my lines of code are running up against like the entire line. Where can I like move stuff onto the next line?
Anytime you want.
Okay. It's basically looking for the semicolon?
Yes.
Okay, great.
Yes. So M+ reads 90 characters across in the syntax, and it will stop reading at that point. And so problems will happen if you type past that, unless it's a comment. You can have comments that go past it, and that won't end up hurting anything.
Oh, okay.
Like,
cool.
it doesn't care about the comments. It will still give you an error message, but it will run it. Where the only situation in which you have to be careful about that is when you start putting constraints. So to foreshadow what we're not getting to today, but what we'll get to on Thursday, which I predicted in my own little head, this is how to do change over time in a latent factor. So actual, like, structural equation modeling with a measurement model involved. And this is going to involve testing invariance first over time. So I have a model that I'm going to show you on Thursday that has 3 outcomes at 4 occasions. We'll do an invariance thing, which is exactly what you already learned last fall, or if you had SN with me a couple of years ago. Trying to get to an example with constraints, though. Okay, so these labels out here are constraints. So that means that BL, 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 that loading, that loading, that loading, that loading are all supposed to be the same number. If I did this, that would break it, because it literally, the constraint label has to be on the same line of code. I know. People are shaking their head. I know. So in that case, I might have to do something like, I could write, if I had like a different one, and then I'd have to re-put it on here like whatever, something like that. Like if I run out of space, then you'd have to go down another line. Like you're allowed to have multiple of the same to make it fit on the lines. But the constraints have to be on the same physical line of code to be applied. Otherwise, it just looks for the semicolon, and you can take as long as you need to get down to where the semicolon is.
I think it's the constraints that I'm running into a problem.
I can take a look at it if you'd like. Yep. You can also stick multiple semicolons on the same line. So like you can do that and condense it that way. But in that case, like you could have a constraint here, no, constraint, and like a different one, like that, and because there's this semicolon is attached to that one, that reads it as a separate command than this one, which is 2 semicolons. So takes a little bit of trickery sometimes to make it not unhappy with you, but
Well, I was just shortening the names of my variables, and
Yeah.
then all of a sudden I'm like, I can't do this much more.
yes, that's the other one. Each variable and each constraint label can only be 8 characters or fewer. So, all right. Well, this is what we're going to do Thursday. How's that sound? Cool. Any questions before we call it a day then with this stuff? No? All right. Well, thanks for hanging in there. I will let you know when we have new stuff available. I'm thinking it's going to be next week. See you all then. See you Thursday.